This is a recast of the 6,200-word piece, Hopfield Networks, from Schnippat AI. This article provides an overview of Hopfield networks, which are artificial neural networks inspired by the human brain's ability to remember and recognize patterns. It discusses their architecture, capabilities, applications, limitations, and potential for hybrid models and interdisciplinary research. Let's listen in.
Today we're diving into the fascinating world of Hopfield networks. These networks are a type of artificial neural network that have gained a lot of attention in the field of machine learning. They were introduced by John Hopfield in 1982 and were inspired by the functioning of the human brain and its ability to remember and recognize patterns.
That's right, Samantha. Hopfield networks are characterized by their ability to store and retrieve patterns in a robust and efficient manner. Unlike traditional neural networks, which rely on feed-forward connections and predefined layers, Hopfield networks are fully connected and operate without layers. Each node in the network represents a binary unit, either on or off.
The connections between the nodes in a Hopfield network are weighted, representing the strength of the relationship between them. These networks employ a dynamic approach where the values of the nodes are iteratively updated based on the inputs received from other nodes. This iterative process allows the network to converge to stable states or patterns from any initial configuration.
And this is where energy minimization comes into play. Hopfield networks utilize the concept of energy minimization, meaning that the network seeks to find the state with the lowest energy level. The nodes update their values asynchronously, following a defined set of rules until the network reaches a stable state called an attractor where the energy is minimized.
The storage and recall capacity of Hopfield networks has been proven to be remarkable. These networks have been successfully applied in various applications such as pattern recognition, optimization, and associative memory retrieval. Their ability to store and recall patterns or memories makes them fundamental in the field of artificial intelligence and pattern recognition.
Absolutely, Samantha. Hopfield networks have found applications in tasks such as image recognition, speech recognition, and data compression. They have also proven to be effective in solving optimization problems, leading to their application in domains like transportation planning, financial portfolio selection, and protein folding. These networks are valuable tools for solving complex problems due to their ability to converge to stable states and resist noise and partial information.
And let's not forget about their capability for associative memory tasks. Hopfield networks can retrieve stored patterns even when presented with incomplete or noisy input. They use a process called pattern completion to fill in missing or corrupted parts of the pattern based on the stored information. This makes them particularly useful for tasks like image and speech recognition.
Absolutely, Samantha. And the simplicity of their architecture and ease of implementation further enhance their applicability in real-world scenarios. Hopfield networks have been applied to solve optimization problems like the traveling salesman problem, where the goal is to find the shortest possible route that visits a set of cities.
That's right, Theo. The unique capabilities and versatility of Hopfield networks make them an important tool in the field of artificial neural networks. Their basic structure relies on binary neurons interconnected by symmetric synaptic weights. The network evaluates the state of each neuron by considering the weighted sum of inputs from all other neurons. The connection weights are updated using the Hebbian learning rule, which strengthens the connections between neurons that fire simultaneously.
This learning rule enables a network to store and retrieve patterns, making it suitable for content-addressable memory tasks. The network exhibits a stable global attractor state, known as an energy minimum, which is reached through an iterative process. The energy function of the network decreases monotonically until it reaches a minimum, representing a stable pattern in the network state.
And there you have it, folks. That's a brief overview of Hopfield networks and their importance in the field of computational intelligence. These networks have remarkable storage and recall capacity, making them valuable tools for pattern recognition, optimization, and associative memory retrieval.
Absolutely, Samantha. And their simplicity and ease of implementation make them applicable in real-world scenarios. Stay tuned for the next segment where we'll dive deeper into the working principles of Hopfield networks.
That's right, Theo. So let's start by talking about the neurons and connections in Hopfield networks. In these networks, each neuron represents a unit of information and can have a binary value of either 0 or 1. The connections between neurons, called synapses, are represented by weights that determine the strength of the connection. These weights are adjusted during the learning process to capture the patterns in the input data.
That's correct, Samantha. The learning process in Hopfield networks involves updating the weights in such a way that the network can store and retrieve specific patterns. Information is transmitted in the network through the activation of neurons based on the input they receive and their corresponding activation functions. The interconnectedness of the neurons enables the propagation of information throughout the network, allowing for the retrieval and recognition of patterns.
Absolutely, Theo. And speaking of activation functions, they play a crucial role in Hopfield networks. The activation function determines the output of a neuron based on the input it receives. In these networks, the most commonly used activation function is the sign function, which assigns a value of either -1 or 1 to the output. This binary nature of the activation function makes it suitable for storing and retrieving binary patterns.
That's right, Samantha. And alongside activation functions, energy functions are also important components of Hopfield networks. The energy function is used to calculate the total energy or cost associated with the state of the network. It evaluates the compatibility between the current state and the desired state of the network. By reducing the energy over time, the energy function helps in updating the state of the network and reaching a stable equilibrium state.
Absolutely, Theo. And when it comes to memory storage and retrieval, Hopfield networks simulate the human brain's memory capabilities. Memory storage involves establishing stable energy states within the network. When a pattern is presented to the network, it attempts to recall the closest stored pattern. Retrieval is achieved by presenting an incomplete or corrupted pattern to the network, and it tries to reconstruct the original pattern based on its stored associations.
That's correct, Samantha. However, it's important to note that Hopfield networks have limitations in their memory storage and retrieval capabilities. They are susceptible to spurious memories, where incorrect or unintended patterns are retrieved. Additionally, the size of memory that can be stored in a Hopfield network is limited, and retrieval of patterns becomes more error-prone as the network size increases.
Absolutely, Theo. Now let's talk about some practical applications of Hopfield networks. These networks have proven to be powerful mechanisms for many applications in various fields. In medicine, Hopfield networks have been utilized to aid in diagnosing diseases and predicting patient outcomes. By inputting symptoms or medical data, the network can compare it with stored patterns and provide a diagnosis or prognosis.
That's right, Samantha. And in the field of computer science, Hopfield networks have been used for pattern recognition tasks, such as character or image recognition. The network can be trained on a set of patterns, and then recognize similar patterns in new data. Additionally, Hopfield networks have also been utilized in optimization problems, where the network can converge to a global minimum.
Absolutely, Theo. The versatility and effectiveness of Hopfield networks make them valuable tools in various fields, contributing to advancements in medicine, computer science, and optimization. One key aspect of Hopfield networks is the Hebbian learning rule. This rule states that when two neurons are simultaneously activated, the connection between them is strengthened. It mimics how the brain learns and forms associations based on experience. This type of learning is considered unsupervised, as it doesn't require explicit feedback. Instead, it relies on the correlation between neuronal firing patterns and the strengthening or weakening of synaptic connections.
That's right, Samantha. Through repeated iterations of Hebbian learning, a Hopfield network can gradually learn and recall patterns, functioning as an associative memory system. However, there are also limitations to Hopfield networks. One major limitation is their learning capacity. As the number of stored patterns increases, the performance of the network decreases. This is often referred to as the network's memory capacity.
And when the number of stored patterns exceeds this capacity, the network becomes more prone to generating spurious states or unintended patterns. This can disrupt the retrieval process and affect the accuracy of pattern recognition tasks.
Another limitation is that Hopfield networks require binary units, which restricts their ability to accurately represent continuous data. Furthermore, storing correlated patterns can be challenging due to the network's architecture. Each neuron is connected to every other neuron, and this can lead to interference among the units.
Despite these limitations, Hopfield networks still provide valuable insights into neural networks and serve as a foundation for further research and improvements in the field. They continue to be used in various applications such as image recognition, optimization problems, and associative memory.
Absolutely, Samantha. Now let's talk about updating and convergence algorithms in Hopfield networks. One common algorithm is synchronous updating, where all neurons update their states simultaneously. This can lead to quick convergence, but also increases the risk of getting trapped in local minima.
An alternative is asynchronous updating, where neurons are updated one at a time or in small groups randomly selected. This increases the chances of escaping local minima, but may require more iterations to converge.
Another convergence algorithm used in Hopfield networks is the use of an energy function to measure the stability of a network. The energy function assesses the total energy of a network and aims to find the global minimum. These updating and convergence algorithms play a crucial role in determining the performance and efficiency of Hopfield networks.
Absolutely, Theo. And one advantage of using Hopfield networks is their ability to function as content-addressable memories. Unlike traditional computers that retrieve information based on specific memory addresses, Hopfield networks store information based on the content itself. This allows for efficient and quick retrieval of relevant information, even in the presence of noise or partial input.
Another advantage is pattern completion. Hopfield networks can reconstruct missing or corrupted patterns based on the information stored in their weights. This makes them particularly useful in applications such as image and speech recognition.
However, there are also some disadvantages to using Hopfield networks. One main limitation is their capacity constraint. As the number of stored patterns increases, the network's ability to accurately retrieve information diminishes. This restricts the scalability of Hopfield networks and makes them less suitable for large-scale memory systems.
Another disadvantage is their sensitivity to initial conditions. Small changes in the network's starting state can lead to different convergence points, potentially resulting in incorrect outputs. This can affect the reliability and consistency of Hopfield networks.
Despite these limitations, Hopfield networks continue to be valuable tools in the field of neural networks, offering insights into computation and memory processing.
That's right, Samantha. One of the key advantages of Hopfield networks is their ability to recognize and categorize complex patterns. This allows the network to efficiently process data and make accurate predictions or classifications. By identifying patterns in large sets of data, Hopfield networks can extract meaningful information and improve decision-making.
Absolutely. And optimization techniques play a crucial role in enhancing the performance of Hopfield networks. These techniques enable the network to find the most optimal solution for a given problem. This is especially useful when there are multiple potential solutions and the goal is to maximize or minimize a specific objective function.
That's a great point, Samantha. Optimization algorithms guide the network towards convergence, improving its ability to find the best possible outcome. This empowers Hopfield networks to tackle a wide range of real-world applications, from image and speech recognition to scheduling and resource allocation problems.
However, scalability and computational complexity are limitations that need to be considered. As the number of neurons in the network increases, so does the computational load. The number of connections between neurons grows quadratically with the number of neurons, resulting in a significant increase in computation time.
That's correct, Samantha. Additionally, the time complexity for updating the state of a network is directly proportional to the number of neurons due to the fully interconnected nature of Hopfield networks. As the network size scales up, the computational complexity becomes prohibitive, making them less suitable for applications requiring large-scale computations.
Another limitation is the memory capacity of Hopfield networks. They can only store a limited number of patterns, approximately 14 to 20% of the total number of neurons. Beyond this limit, the network becomes prone to spurious states and pattern recall errors.
Despite these limitations, Hopfield networks have been extensively studied and compared with other neural network models. One major point of comparison is the energy function used by Hopfield networks. Unlike other models such as feed-forward neural networks, which use a simple summation of input values multiplied by weights, Hopfield networks employ a quadratic energy function.
That's right, Theo. This quadratic energy function allows Hopfield networks to model complex relationships between input patterns, making them more flexible and powerful for solving problems like pattern recognition and optimization.
Absolutely. Hopfield networks have also been compared to other recurrent neural networks, such as the Elman network and the Jordan network. While Elman and Jordan networks excel in sequence learning tasks, Hopfield networks have shown superior storage and retrieval capabilities for associative memory tasks.
And let's not forget about the real-world applications of Hopfield networks. They have proven to be effective in various domains. For example, in image recognition and retrieval systems, Hopfield networks can recognize distorted or incomplete images and provide the closest match or retrieve similar images from a database.
That's right, Samantha. Hopfield networks have also been successfully utilized in optimization problems like the traveling salesman problem, TSP. By encoding city locations as network states and minimizing the overall energy of the network, Hopfield networks can offer approximate solutions to the TSP and other optimization problems.
And let's not forget about pattern classification tasks. Hopfield networks have been used for speech recognition and handwriting recognition. By training the network with a set of patterns, it can classify new, unseen patterns with remarkable accuracy.
Overall, the versatility and efficacy of Hopfield networks make them valuable tools for solving real-world problems in various domains.
Absolutely. And one of the key concepts behind Hopfield networks is associative memory. It's the ability to recall a memory or pattern based on partial cues or related cues. It's like recognizing a face or familiar object, even with changes in lighting or perspective.
Right. And this is achieved through interconnected processing units, or neurons, in network. These neurons communicate with each other through weighted connections that are learned through a process called Hebbian learning.
Yes, Hebbian learning strengthens or weakens the connections between neurons based on their co-activation. So when presented with a partial cue or noisy input, the network can converge to a stable state that represents the complete memory or pattern.
And this concept of associative memory has been applied in various applications such as optimization problems, content-addressable memory, and error correction. Hopfield networks have been particularly successful in solving combinatorial optimization problems.
Combinatorial optimization is about finding the best solution from a finite set of possibilities. And Hopfield networks excel in this because they use interconnected nodes that simulate the behavior of neurons and synapses in the human brain.
Exactly. These networks employ an energy function to minimize the cost of the system and reach a stable state that represents the optimal solution. This makes them valuable in real-world scenarios like finding the shortest route in a transportation system or determining the optimal allocation of resources in a supply chain.
But it's important to note that Hopfield networks have their limitations too. They struggle to scale well with a large number of neurons and are sensitive to noise and easily get trapped in local minima.
That's right. However, researchers have proposed enhancements to address these challenges. Some of these enhancements include incorporating probabilistic elements or dynamic learning rules that adjust network connectivity.
And another potential solution is the integration of other machine learning techniques, like deep learning. This could help overcome the scalability problem and further improve the performance of Hopfield networks.
Absolutely. The future of Hopfield networks looks promising. They have the potential to revolutionize various fields by providing efficient and robust solutions to complex problems.
Exactly. Deep learning, which is a subfield of machine learning, focuses on building artificial neural networks that can learn and make intelligent decisions. By incorporating deep learning techniques into Hopfield networks, we can not only store and retrieve patterns, but also understand complex relationships and make predictions.
That's right. Deep learning algorithms, such as deep neural networks, can be used to train the weights of the Hopfield network. This enables the network to better generalize and recognize patterns. The combination of deep learning and Hopfield networks has already shown promising results in applications like image recognition, natural language processing, and speech recognition.
And by leveraging the power of deep learning, Hopfield networks can overcome limitations associated with storage capacity and noise tolerance. This means they can perform even better in practical real-world scenarios.
Absolutely. The incorporation of deep learning techniques opens up a whole new realm of possibilities for Hopfield networks. It enhances their capabilities and makes them even more attractive for a wide range of applications.
Another fascinating aspect of Hopfield networks is their potential for hybrid models and interdisciplinary research. Hybrid models can combine different types of artificial neural networks or incorporate non-neural algorithms to tackle complex problems more effectively.
That's right. For example, hybrid models can combine Hopfield networks with convolutional neural networks, CNNs, to improve image recognition tasks. By leveraging the memorization and associative memory properties of Hopfield networks, hybrid models can enhance the accuracy and reliability of CNNs.
And interdisciplinary research is crucial in exploring the full potential of Hopfield networks. Researchers from various fields, such as computer science, neuroscience, and physics, can collaborate to develop new algorithms, analyze the underlying principles, and understand the limitations and capabilities of these networks.
Absolutely. By fostering such interdisciplinary collaborations, we can explore new frontiers in cognitive science and artificial intelligence. This paves the way for advancements in fields such as data analysis, pattern recognition, and optimization.
And we've already seen the promising results of Hopfield networks in various applications. They have been successfully used in pattern recognition tasks to classify and detect objects based on visual features. The network is trained with a set of input patterns and adjusts the connection weights to minimize the energy function. Once trained, it can accurately recognize and classify new patterns, even in the presence of noise or partial information.
That's right. Hopfield networks have also been employed in optimization problems, such as finding the shortest path in a graph or solving the traveling salesman problem. By encoding the problem into binary variables and defining an appropriate energy function, the network can iteratively update its state to converge to the optimal solution.
And let's not forget about associative memory tasks. Hopfield networks have proven to be useful in storing and retrieving information based on given cues or patterns. This is achieved by training the network to associate specific patterns with specific outputs.
Indeed, Hopfield networks have shown their versatility and effectiveness in various real-world applications. From pattern recognition to optimization and associative memory tasks, they have provided valuable solutions to complex problems.
However, it's important to note that Hopfield networks do have their limitations. For example, they require symmetric connectivity and can have spurious states. But researchers are continuously exploring and enhancing the capabilities of Hopfield networks.
That's right. Modern variants like the bidirectional associative memory, BAM, and stochastic Hopfield networks address some of these limitations and offer more efficient and robust performance.
And the application of Hopfield networks in areas such as image and data compression, optimization of energy usage, and neural computing demonstrates their utility and potential for further advancements.
Absolutely. Hopfield networks provide a valuable framework for addressing complex problems. They continue to inspire research in the field of neural networks and artificial intelligence.
In conclusion, Hopfield networks are a powerful tool for solving optimization problems, pattern recognition, and associative memory tasks. They've already proven their effectiveness in various applications, but there is still room for further improvement and innovation.
Continued research and innovation in Hopfield networks are crucial to address their limitations and unlock their full potential. By exploring new algorithms, techniques, and interdisciplinary collaborations, we can further enhance the capabilities of Hopfield networks and pave the way for novel applications in various fields.